Good morning. How are you? Perfect. So let's welcome to my session about deadlocking in SQL Server. So in the next 90 minutes, I want to cover a lot of different things in SQL Server, why deadlocks can occur in SQL Server, how we can detect, analyze deadlocks in SQL Server, and finally, how we can resolve them. A few words about my person. My name is Klaus Aschenbrenner, and I provide with my company SQL Passion, SQL Server consultancy and training services across Europe. I'm also a Microsoft Certified Master for SQL Server 2008, which was the highest technical certification that you could have achieved for SQL Server. I say was because Microsoft just retired that certification because they have made no profit out of it. So really strange story. I'm also the author of the book Pro SQL Server 2008 Service Broker. This book was published in summer of 2008. Service Broker is an asynchronous messaging framework that Microsoft first introduced back with SQL Server 2005. And with Service Broker, you're able to write asynchronous message-based database applications. Who of you is working with Service Broker? Almost nobody. So as you can see, I'm just working with things that nobody cares about. No, just kidding. You can also follow me on Twitter, and further information about my person, my services that I'm offering, you can find them on my website at sqlpassion.at, where you also find more free training content around SQL Server. Let's have a look on the agenda. Who of you is already familiar with the various isolation levels in SQL Server? Okay, so some of you. In the first part, I just want to give you a brief overview how isolation levels in SQL Server are working, because we need that information later on when we talk about deadlocking, because it's very, very important that you understand the semantics of the chosen isolation level, because otherwise it's sometimes very, very hard to understand why a specific deadlock occurs in SQL Server. So the first step, just a few words, a few examples about isolation levels in SQL Server. Here we will already see some interesting things that are happening in SQL Server, and afterwards we will continue by talking about deadlocking itself in SQL Server. When we talk about transactions in SQL Server, every transaction in a relational database has the ACID properties, means we want to have atomic transactions, consistent ones. Transactions should be always isolated from each other, and finally they should be also durable, means when our database crashes we don't want to lose any transactions. When we talk about isolation levels, we always talk about the isolation property, means with the transaction isolation level we are able to influence how much isolation we want to have between concurrent queries in SQL Server. When we look on SQL Server itself offers us two different concurrency models, a so-called pessimistic one and an optimistic one. The pessimistic one is already forever implemented in SQL Server, and the pessimistic concurrency model just means that SQL Server uses internally locking to isolate sessions, queries from each other. When we talk about queries, we have always two kinds of queries in a database. We have queries that are reading data, means our select statements, and we have queries that are changing data, our insert, update, and delete statements. And with the chosen isolation level, we can influence how long readers are holding their shared logs. Means every time when we read data, SQL Server acquires a so-called shared log on that specific record. Every time when we change a record, SQL Server acquires an exclusive lock on that record, and both locks are just incompatible to each other. Means when you have a shared lock on a record, you can't concurrently change that record because the acquiring of the exclusive lock is blocked by the shared lock. When you have an exclusive lock on a specific record, maybe you have already a transaction which tries to update that record, then you can't concurrently read that record because in that case the update blocks the reader, the select statement. And when we choose the isolation level in SQL Server, then we influence our readers, our select statements, how long those select statements are holding their shared locks. We have no influence over our writers, over our insert, update, and delete statements. Those statements will always acquire an exclusive lock. We can only influence the readers through the chosen isolation level. And in addition, since SQL Server 2005, we also have a so-called optimistic concurrency model. Optimistic concurrency model was introduced back with SQL Server 2005 and uses internally a row version technology. Means an optimistic approach that, for example, Oracle uses since ages. So it's nothing that Microsoft just has invented, just a thing that Oracle already do forever. Optimistic concurrency just means that a reader, a select statement, doesn't acquire a shared lock anymore. Means when we read a record, SQL Server reads the version of that record from the version store, and the version store is held in DempDB. We always refer to DempDB as the public toilet in SQL Server because all the bad things are happening in DempDB in SQL Server. Means when you are using optimistic concurrency, you also have to carefully plan and size your DempDB accordingly. With optimistic concurrency, we have two isolation levels: read committed snapshot isolation, which is just an optimistic implementation of read committed, and we have a completely new isolation level called snapshot isolation. We will also see them later when we are talking about deadlocking, because with an optimistic concurrency model, you can also eliminate deadlocks in SQL Server very, very easily, because normally you have very, very often deadlocks between readers and writers. Means when you eliminate the shared lock that readers, our select statements, are acquiring through an optimistic concurrency model, then you have already eliminated a huge amount of different deadlocks that can occur in SQL Server. When we talk about pessimistic isolation levels, we have 4 different isolation levels. Our default isolation level is always read committed. Means when you don't specify a specific isolation level, your transaction just runs in read committed. As I've said previously, when we choose the isolation level, we just influence how long a reader, a select statement, is holding their shared logs. In read committed, SQL Server only holds the shared log when we read a specific record. Imagine we have a table with 5 records. When we read from that table, we read the first record, then SQL Server acquires the shared log on that record. When we have processed that record, SQL Server releases the shared log. Then we move on to the second record. SQL Server acquires the shared log on that record, reads the record. When we have read that record, we release immediately the shared log. Means we are only holding that shared log as long as we need it during the reading of the record. Means with read committed, you have no so-called read stability. Imagine you are reading these records multiple times in your transaction. Because you are releasing your shared log immediately, someone else can change that record during your transaction. Means when you later on read the same record again, you can get different information. You have no read stability. Therefore, we have the isolation level repeatable read. With repeatable read, we acquire our shared locks when we read the record, and we only release that shared lock at the end of our transaction. When we perform our commit or rollback, means when we are holding our shared locks till the end of the transaction, it means that nobody else can change that record, because the exclusive lock is blocked by the shared lock. Means we have achieved a read stability. We can read these records multiple times and we always see the same information. We also have the isolation level read uncommitted. In read uncommitted, we don't acquire any shared locks. Really, really bad, because you can have dirty reads. You can read transient data from transactions that are currently not yet committed. Imagine that. Not really useful. It's the same as the no-lock query in SQL Server that you can specify. Who of you has already used no-lock? Everyone. It's fast. But even no-lock can block. Just think about that. And finally, we have a fourth isolation level called Serializable. And with Serializable, SQL Server tries to make a range of records stable so that we have a so-called phantom avoidance. Imagine you have a select statement, and with that select statement you retrieve all your customers from UK. By default, when you're in the isolation level read committed or repeatable read, some other transaction can insert a new record into that range. Means when you're doing that select statement again in your transaction, you retrieve your customers from UK, maybe you see one additional record, a so-called phantom record. And if you don't want to have that behavior, then you can use the isolation level Serializable. And with Serializable, SQL Server internally uses a so-called key range locking technique. And with that technique, SQL Server makes sure that that range of record remains stable. Means nobody else can insert a record into that range, nobody else can delete a record from that range, nobody else can move an existing record from outside the range with an update statement into that range. That's the isolation level Serializable. Most important thing here is it's a key range locking technique, means you need a supporting non-clustered index. In our case, on the column country, where country equals UK. When you have no supporting non-clustered index, SQL Server has to lock your entire table, which is really, really bad, because you can't do anything with your table anymore. So here it's very, very important that you have a supporting non-clustered index. Optimistic isolation levels, as I've said, were introduced back with SQL Server 2005. We have two new isolation levels. Read committed snapshot isolation, which is just an optimistic implementation of the isolation level read committed. And we have a completely new isolation level snapshot isolation, which mainly provides you the characteristics of the isolation level Serializable. Both isolation levels are based on row versioning, means when we read data through select statements, the select statement itself doesn't acquire a shared lock anymore, because we just read the version which was valid at the beginning of that statement from DempDB, from the version store, and therefore we can eliminate that shared lock. You can eliminate a huge amount of different blocking scenarios, and as I've already said, you can also eliminate a huge amount of different deadlocks that can occur in SQL Server. I have here a nice table which just shows you the various isolation levels in SQL Server and which phantoms or which problems in each isolation level can occur. For example, as you can see, with uncommitted, almost everything is possible, even dirty reads. You are just able to read uncommitted data. When you look at the isolation level Serializable, no symptoms are possible anymore. means you also have to choose your isolation level accordingly. You can't run every transaction with uncommitted because you just return inconsistent data. On the other hand, your performance would be great because there's no blocking, no locking. On the other hand, you can't run every transaction in the isolation level serializable. You would get back really, really good consistent results, but on the other hand, you would have a really, really bad performance because a lot of blocking situations would occur. Therefore, for every transaction, you also have to think about which isolation level you should choose based on the symptoms that you want to have or you want not to have. When we talk about the various locks in SQL Server, we have the shared lock, which is acquired by our select statements. We have an exclusive lock, which is acquired when we perform insert, update, delete statements. And in the middle of the two, we also have a so-called update lock. When we look at an update execution plan in SQL Server, the first thing when you update a record is that you have to find that record. So every update execution plan consists mainly of two phases. In the first phase, you're searching for the data that you want to update, and in the next step, you update that data. And during the finding phase, SQL Server uses a so-called update lock. Means an update lock is not compatible with an update lock. But an update lock is compatible with a shared lock, means during the finding phase of your data, other select statements can still read your data. And finally, when you have found that data, then the update lock is converted to an exclusive lock. And as we will also see later, the update lock is also needed to prevent some kinds of deadlocks. When you work in an update execution plan just with a shared lock in the reading phase, you could introduce a huge amount of different deadlocks. We'll also see that later. So as you can see here from that matrix, as soon as an exclusive lock is involved, you always have to wait. That's the main outcome. When you change a record, when you perform an insert, update, delete statement, that record is exclusively locked. Means when someone else wants to read that record, you immediately have to wait. Let's have a look on the isolation levels. I don't cover every isolation level, just the most important ones that we need for deadlocking itself. In the first step, I just want to work with the default isolation level of read committed. As you can see here, I'm just beginning a new transaction and updating the record with the business entity ID of 1. Just the first record in that table. When you want to read that record from another session, you have to wait. So that's just a traditional blocking scenario in SQL Server. Means in that case, the update statement just blocks the select statement. You can also see in system logs which session is holding which locks in SQL Server. So when we go here a little bit down, you can see we have two locks on a key, on an index key. We have one exclusive lock from session ID 52, and session ID 53 just waits on a shared lock. So just a traditional blocking scenario in SQL Server. Means when you finally commit or roll back your transaction, you release your exclusive lock, means the other session acquires the shared lock and can continue. And that's also the problem with locking and blocking. In that case, that SQL statement took around 1.5 minutes. When you rerun that SQL statement, it's very fast. That's just blocking. So just imagine that when you have a slow query in SQL Server, it normally not means that you have only problems with your indexing strategy. Maybe you had a blocking scenario. Just think about that. So as you can see in the default isolation level of read committed, it's very, very easy to get into blocking situations. Next step. I have here another session, and I'm setting here the isolation level to repeatable read. Means we want to have a read stability. Means when we read our data multiple times in the transaction, we always want to see the same information. Means in repeatable read, SQL Server now holds the shared logs till the end of our transaction. So I begin here a new transaction, and now I run a simple select statement. I just retrieve 6 records, means SQL Server has locked those records and still holds these shared logs. Means when another transaction, like an update statement, wants to read those records from the table person.person, it blocks. So in that case, our select statement, our reader, blocks the writer, our update statement. Just the other way around. Means when we are holding our shared logs, we can read that data multiple times. Nobody else changes that data, because the data change is blocked. Means we have our read stability.
Quick question. So you've set the transaction isolation level at the top.
Yeah.
What if someone's used the no lock hint on the select statement?
In that case, you're just overriding the isolation level and you don't acquire shared logs.
Just for that?
Yeah.
Just for that one
Yeah.
statement?
Means in that case, you are running that statement in the isolation level with uncommitted. The most important thing here is you need a supporting index on the column modified date, because SQL Server needs something, some physical resource to lock. In our case, index keys. As you can see, we have here a supporting non-clustered index. Means here SQL Server physically just locks these 6 individual records. When you have no supporting index and you perform, for example, in the execution plan a clustered index scan, then SQL Server locks every record in your table, because physically you needed to read the complete table to find these 6 logically requested records. Just think about that. Your indexing strategy also influences how SQL Server is doing the locking and blocking internally, which is also very, very important for resolving deadlocks. You can resolve deadlocks by applying a good indexing strategy, because with an additional index, you provide SQL Server an additional data access path with which SQL Server can retrieve that data. An index is just an additional road through which you can retrieve your data, nothing more. Means with multiple roads to your data, you have no traffic jam. Okay? When we look here, session ID 53, and we go again to system trend logs, and we restrict again on our key logs. You can see we have just logged a few rows here, not too much. because we have for that statement a supporting non-clustered index. Finally, when we commit that transaction, we release our shared logs, means our update can continue because now we are able to acquire that log.
If you don't define a transaction for the reads, for example, what sort of logging does it do?
By default, you have the isolation level read committed.
So even if you don't do a begin transaction?
When you don't begin your transaction, you still run in that case. That transaction in the isolation level repeatable read means you have a so-called auto-commit transaction in SQL Server. SQL Server internally begins your transaction, you read, you make your select statement, and finally SQL Server commits it.
Yeah.
Means in that case you are not able to reproduce that blocking scenario because SQL Server immediately commits your transaction and you release your shared logs. For example, I'm hinting here SQL Server with the clustered index. Means I'm just telling SQL Server when we read here data, we want to read the data through the clustered index. Means as you can see we have a clustered index scan with a predicate which just discards non-qualifying rows. Interesting thing, when we look again to system20 logs, you have here not just a few records because SQL Server has escalated those individual shared logs on the table level. When you have on the record level more than 5,000 logs, then SQL Server triggers internally a log escalation, means those individual shared logs are escalated to one shared table log. Means you have a table which is read-only, because you have logged your complete table with a shared log and not only the range that you have requested here. Just think about that. So retrieving or reading a huge amount of rows in the physical execution plan can also trigger log escalations in SQL Server. Therefore, very, very important when you work in the isolation level repeatable read or even serializable that you have a good indexing strategy so that SQL Server can use here a supporting non-clustered index to find those matching qualifying rows. Okay. Just want to show you one additional example about the isolation level read or read committed snapshot isolation. At first, you have to enable read committed snapshot isolation. Means when you enable it, then our new default isolation level is read committed snapshot isolation. Means using read committed snapshot isolation is completely transparent to your applications. It's just a database option, and now your new default isolation level is read committed snapshot isolation. Just an optimistic implementation of the isolation level read committed. So for example, I begin here again a new transaction, default isolation level, read committed. In our case, read committed snapshot isolation. And I'm updating here a specific record. Means when we here update a specific record, SQL Server copies the old version of that record over to the version store, which is held in TempDB. Means when we have another transaction which wants to read that data, we just read the data from TempDB without acquiring a shared log. Just think about that. There is no blocking anymore. Previously, as you have seen in read committed, that select statement was blocked by the writer. Now in that case, we just read that version, that previous version from TempDB. Means with read committed snapshot isolation you can overcome or resolve a huge amount of blocking situations and therefore also a huge amount of various deadlocks that can occur. Just think about that. So read committed snapshot isolation, a very, very important isolation level when you have a huge amount of deadlocks.
Is there a performance impact to that? 'Cause obviously
Of course.
it's
Of course it costs you performance, because when you have an update or delete statement, that specific statement must copy the old version to DempDB. When you perform an insert, there is no old version, it's just a new insert, a new record. Means your update statements, delete statements are just introducing additional CPU overhead. And of course, the select statements, your readers have to find the corresponding version from version store, which also includes additional CPU overhead. So you have CPU overhead, and of course you also have storage overhead in DempDB. Means you also have physical I/O in your DempDB, means you should also put DempDB on fast performing drives. So DempDB sizing and planning is here very, very important.
And so is there a way to enable it without making it default for a database?
Sorry?
Is there a way to enable it without actually making it the default on the database as well?
Well, it's just a default, it's just an option on the database. So as soon as you set that option read committed snapshot to on, then every transaction uses the isolation level read committed snapshot.
And you use it on a per transaction basis?
Every time when you execute a session, every time. Because the default isolation level is read committed snapshot. Means when you don't specify explicitly your isolation level, you use read committed snapshot. Just an optimistic implementation of the default pessimistic isolation read committed. So you still have the semantics of read committed, just solved in an optimistic way. Other questions?
Is there any guidance that you could give on when you would choose to do that based on how many reads compared to insert, update, deletes? Is there any kind of, if you're doing 95% of your database is read only, would you choose that?
Not really.
No.
There's no guidance.
magic.
No guidance. As I've said previously, optimistic concurrency is just a concurrency model that Oracle uses since ages. So when you show the first demonstration with read committed, that an update statement blocks a select statement, to Oracle guys, they're just telling you, you are insane with SQL Server, move to Oracle and your programs are just gone. So it's just a default behavior in Oracle. As I've said, it's nothing that Microsoft just has invented. Mainly they have invented and implemented it in SQL Server so that it is easier to move Oracle workloads to SQL Server. Okay. This was just a short introduction to isolation levels in SQL Server. Let's move now on with deadlocking itself. The nice thing about deadlocks is that SQL Server itself finds out if there are deadlocks. In SQL Server we have a background process called the Deadlock Monitor. That Deadlock Monitor runs every few seconds, goes to the log manager, looks on the individual logs that we currently have in our system and checks if there is a deadlock or not. If there is a deadlock, then the Deadlock Monitor rolls back the cheapest transaction. The cheapest transaction is always that transaction which has written the less bytes into the transaction log. So for example, when you have a deadlock between an update statement and a select statement, SQL Server will normally roll back the select statement because the select statement hasn't written any information into the transaction log. So that's the cheapest transaction. That transaction which has written the least amount of bytes into the transaction log. When the deadlock was occurred, the transaction which was rolled back gives us the error message 1205. Means we as developers should always check if we got that specific error number from SQL Server. Because a deadlock situation is a situation from which we can fully recover without informing our end users about that specific program. The only thing that we do is the following. We check if we got that error message number. If yes, we wait a few seconds so that we give the other transaction some time to continue and finally commit or roll back its work. And finally, we just retry our transaction. Very simple, yeah?
Can you suggest a strategy for how long to pause?
No. Depends on the other transactions. Maybe your other transaction is a transaction which completes in a second. Maybe your other transaction is a transaction which needs 5 hours. Depends on your workload. Of course, you should not do that in a while loop forever. So at some point in time, let's say after 10 retries, you should also implement some logic where you just give up and inform your end user that we have some programs, okay? So not just do that in a simple while loop forever. How can we troubleshoot deadlocks in SQL Server? We have multiple ways. SQL Server Profiler. SQL Server Profiler provides us an event called deadlock wave, and that event returns us a deadlock wave. The deadlock wave itself is just an XML document, and that XML document describes between which processes the deadlock occurred and between which resources. So with that XML document, we are able to find out why we had a deadlock in our system. There's also a trace flag, 1222, which writes that XML format into our error log. I'm not really a big fan of it. Just show you that. Looks like that. Means you have an XML document, and SQL Server just writes with that trace flag, that XML document, line by line into the error log. Not really useful. You know here, okay, we have a deadlock, but analyzing that deadlock from the error log, no, we don't want to do that. When you are on SQL Server 2008 or higher, you also have extended events. Extended events is a new lightweight tracing infrastructure that Microsoft first introduced back with SQL Server 2008. And with extended events, you have a session called the system health session, which just always runs. And within that system health session, SQL Server also logs historical deadlocks. Deadlocks that have occurred since the last restart of SQL Server. So when you're on SQL Server 2008 and higher, it's very simple to look into that extended event session to find out if you had deadlocks or not. So normally, when you're on SQL Server 2008 and higher, you don't really need that trace flag anymore. Just use extended events to find out if you had deadlocks or not. We'll also see that later. SQL Server Profiler provides us the deadlock wave, which is just a simple XML document. Means you have here a process list. The process list tells you between which processes you had a specific deadlock, and the resource list tells you between which resources, for example, between which tables, which indexes you had that specific deadlock. That deadlock can be also, that deadlock wave can be also visualized within SQL Server Profiler or also within SQL Server Management Studio. Normally, you will work with the XML itself because the XML just provides you more information as the visualization itself. The visualization itself is nice to get a big picture what happened for that specific deadlock. If you want to find out further more detailed information, normally you work with the XML itself. We'll also see that later. We've already talked about traceflag 1222. Normally not needed anymore when you're on SQL Server 2008 and higher, because we have extended events, that system health event session, and SQL Server just tells us when a specific deadlock occurred on our system. Okay, last slide. Let's produce some deadlocks. We start very, very simple. I have here a simple so-called cyclic deadlock. Means I create here in tempdb 2 tables. Every table just has 1 record. And in the first session I begin a new transaction and update table 1. In the second session we go to the public toilet of SQL Server and we update the second table. Means every session has an exclusive log on a record in the other table. In the next step, I'm trying to update table T1. Doesn't work, because we have already in the other session an exclusive log on that record. Means in that case, a writer blocks a writer. Just a traditional blocking scenario. That's not a deadlock. When we roll back that transaction, when we commit that transaction, everything was fine. Let's go now to profiler. And we have here logs, deadlock graph. So what we do now in the next step, in the first session, I'm updating table T2. We can't acquire that exclusive log because the first session has already an exclusive log. Means now we're in a deadlock because everyone waits on the other one. So when we do that update statement, both are waiting. And as you can see, we were now very, very fast. And SQL Server has chosen the second session as the deadlock victim. Means the second session was rolled back. Error message number 1205. There's no active transaction anymore. Means, as you can see, when we now try to make a commit or rollback, SQL Server tells us there's no active transaction anymore. So that transaction was rolled back. Means we also have released the exclusive log on the second table. Therefore, the first session was able to acquire that exclusive log. And finally, we are able to commit or roll back our transaction. And as I've said, just rerun your transaction. So we have now paused some time, the other transaction completed in the meantime, and now we just rerun our transaction. Means a deadlock is a situation from which you can fully recover automatically. And SQL Server Profiler has logged that deadlock. That deadlock graph can be exported. Extract deadlock event. Those files have an extension of XTL. And we can also open it within SQL Server Management Studio. As you can see, we have here the deadlock. SQL Server tells us we have a deadlock between session ID 53, 52. Session ID 53 was our deadlock victim, crossed out. You can see session ID 52 had an exclusive log on a specific record, requested an update log on table 1, and session ID 52 had an exclusive lock on the first table and requested an update lock on the second table. Okay? We can also look on the XML. So let's open that with the XML editor. And that's now already more interesting than the graph itself. As you can see, it's not that hard. You have a process list and you have a resource list. Means within the process list we can see which processes were involved in that specific deadlock. So for example, you can see here lock used. Those are the number of bytes that were written into the transaction log for the first process. Means our first transaction wrote 144 bytes into the transaction log, the second one 224 bytes. You can also see on which resource you have waited. In that case, we have dealt with a heap table, with a table without a clustered index, because we have waited on a row identifier, and the row identifier is only used in a heap table. Database ID 2, tempdb, first file, page ID 147, and on that page the first record. So you already know here a huge amount of information. You have your wait time, how long you have waited. You see when your transaction was started. What else do we have? Your client application, when you provide that information in the connection string. And SQL Server also tells you the isolation level, which is also very, very important. Of course, when you lower down your isolation level, as we have said previously, you introduce more blocking and therefore also more possibilities for deadlocks. And you have your database ID, database ID 2, tempdb. You have that information for the second process. You can also see which statement you have executed. And when we look down, we now also have the resource list, and the resource list tells us on which resources that deadlock has occurred. We have here a row identifier log, means we have dealt with a heap table, a table without a clustered index. Again, you can see file ID, page ID, database ID. You have the object name. And then, when we go to the right, you just have the associated object ID. That's just the object ID of that table. So with that object ID, you can also find out on which table that deadlock occurred. And you have now a owner list and waiter list. Means SQL Server tells you process 848, the second one, had an exclusive lock. And the process C28, the first one, waited on an update lock. And when we look on the second resource, you can see that the process IDs are just exchanged. Means the first process, C28, had an exclusive lock, and the second one, 984, waited on the update lock, that lock. Yeah?
Why do the process IDs have an extra digit on the end?
I have no idea. I have no idea. I also wonder now. I have no idea why the last digit is missing here. Ah, it's just because we have collapsed it.
I like it.
Nothing more. No idea why SQL Server Management Studio is doing that. So process ID is there correctly, but it's just truncated a little bit when we collapse that XML element. Yeah. So it's still there. Okay. So as you can see, working with that XML, very, very easy to find out where you had here that deadlock. In addition, we have extended events. As you can see, we have here system health event session, and that system health event session runs always. Means when you're in SQL Server 2008, every one of you is using extended events. And within that system health event session, SQL Server logs all the deadlocks that have occurred since the last restart of SQL Server. So, I show you one query. When I find it. And this is a simple query which goes to that system health event session and just extracts through xquery all deadlocks that were reported to that event session. And as you can see, we had one deadlock a few minutes ago. And again, you have your XML document. Just think about that. So you even don't need profiler. Because with extended events, every historical deadlock is logged in that extended event session system health. So very easy to find out if you have deadlocks or not. Just execute that query and check that. A huge amount of applications have deadlocks and they even don't know it. Okay? Even SQL Server Management Studio sometimes introduces deadlocks. Okay? Let's continue. Who of you has attended yesterday my session about bookmark lookups in the evening? Okay, just one, that's perfect. Because now I can also show you that bookmark lookups in an execution plan can cause deadlocks. I create here a simple database with a simple table. I create a non-clustered index on the third column called 3. I insert a few records, and we have here that record. What I'm doing here, I have here a simple update statement which changes the clustered key value. When you change your clustered key value, SQL Server has to update the clustered index, and in addition SQL Server also has to update the non-clustered index because the clustered key value is always part of the non-clustered index. And when you have a concurrent transaction which executes a query which causes in the execution plan a bookmark lookup, then both transactions can deadlock against each other. Imagine what happens here. We are seeking into that non-clustered index, means SQL Server acquires a shared lock. In the meantime, we are running that execution plan. That execution plan acquires an exclusive lock on our clustered index. Then that plan continues and tries to update the non-clustered index by acquiring an exclusive lock. That exclusive lock on the non-clustered can't be acquired because our other session has already the shared lock on the non-clustered. Means our update execution plan just waits. And in the meantime, our select statement continues and tries to acquire a shared lock on the clustered index. We can't get the shared lock on the clustered index because the other session has already acquired the exclusive lock on the clustered index. That lock between both sessions. I'm just helping here SQL Server a little bit by setting the isolation level to repeatable read so that we are holding our shared logs longer. It's just easier to reproduce the deadlock. When you're running or when you have a production workload, it's also very, very simple to have a deadlock in the isolation level read committed. I'm just helping here SQL Server, means we are running both sessions just in a while loop, and it takes now a few seconds and one session will be rolled back. Boom. Query completed with errors. As you can see, we have again a deadlock. Resolving that deadlock is very, very simple. Provide a covering non-clustered index. By providing a covering non-clustered index, SQL Server has no need in that execution plan to access the clustered index through the key lookup, and therefore the deadlock will be resolved. So for example, let's say we just retrieve here call 2 and we change our index definition to include call 2 in the leaf level. We can run both sessions forever without any deadlock. They will run forever without any deadlock. So as you can see here already, your indexing strategy influences the deadlock behavior of SQL Server. By providing a good indexing strategy, you can also eliminate deadlocks. Another option here would be to use the isolation level read committed snapshot isolation. Because with read committed snapshot isolation, we have no shared logs anymore, means there's also no deadlock. So two ways how to deal with that problem. Let's stop that. Let's stop that. And let's recreate that non-clustered index without the included column. Let's make again the select star, and let's switch that database to read committed snapshot isolation. So let's change that to read committed snapshot. And now I'm just reconnecting in every session so that we are using the default isolation level of repeatable read. Because I have set the isolation level, the default isolation level of read committed, because we have set previously the isolation level to repeatable read. So we just reconnect in every session. And now, when we again run our endless loop, you will also see that there will be no deadlock anymore. So enabling read committed snapshot isolation can be also one way how to deal transparently with a huge amount of different deadlocks. You don't have to change anything. It's a database option, and 80% of your deadlocks are just gone. Just think about that. Question?
So you mentioned with the pessimistic isolation levels, it's the developer should check for a particular error.
Yeah.
So a particular exception being thrown, and then pause and retry the transaction.
Yeah.
So if you're using an optimistic currency isolation
Yeah.
doesn't the developer have to, although deadlocks are less likely, doesn't the developer have to check for optimistic concurrency exception?
Nothing. When you are using read committed snapshot isolation, no. When you use the completely new isolation level, snapshot isolation, then you can have so-called update conflicts.
Right.
And you have to check on those update conflicts because that's just a new error message that SQL Server can return you. But here with read committed snapshot isolation, nothing happens. You have no side effects.
You can't get an update conflict.
No, it's not possible because read committed snapshot isolation means you're getting back the version of the record that was valid at the beginning of your statement. So you have a statement level row versioning. With snapshot isolation, you get back the version of the record which was valid at the beginning of your transaction. Means you have a transaction-based row versioning. And here you can have update conflicts. But with read committed snapshot isolation, you have no side effects. As you can see, both sessions are still running without any deadlock. So just two ways how to deal with that specific deadlock. Provide a covering non-clustered index so that we can eliminate that bookmark lookup that we see in the execution plan, or set the database to read committed snapshot isolation so that readers do not acquire shared logs anymore, means we can also overcome that specific deadlock very, very easy. Now maybe, no. So, let's talk about deadlocks that can be caused by missing indexes. Just think about that. You have a query, you are missing an important index, and because of that, you have a deadlock. I create here a simple table and I insert 4 records. Second table, I also insert 4 records. We have on both tables no supporting indexes. Means when we make here, for example, an update statement, SQL Server has to read the complete table with a table scan operator to find the qualifying rows. As you can see here, we have again a predicate where we check if column 2 equals to 1. Means we have to read the complete table to get here the first row from that table. So let's start that first transaction. In the second transaction, I'm doing the same with the second table. I request here logically the second row from that table that we have inserted. As you can see, where column 2 equals 2. Again, in the execution plan, we have to scan the complete table to get to the second row. Means SQL Server scans the first row is returned, reads the third row and fourth row. And now the fun begins. From the second table, I request the third row, a different row. As you can see here, we have an exclusive log on the second row. And now we request from that table the third row, a different row. But that statement will block. Why? Why is that statement blocking?
Because it leads to rows.
Sorry?
Because it has to scan all rows.
We have to go through all rows to get to the third row. Means you have to pass the second row, which is currently blocked. Therefore, we have here a blocking scenario. It's not a deadlock by now. Just imagine that a scan is always a scan. Even when you logically request a different row, you have to read some other rows. When those other rows are currently locked, it leads to a blocking situation. And now in the other session, I'm just reading from the first table the fourth row. Of course, when we read the fourth row, we have to go through the first row, which is currently blocked or locked, means we are also locking here. And now we have again a deadlock. Everyone waits on the other one. How can we solve that deadlock? With an index. So what I'm doing here, I create on both tables a non-clustered index on column 2. Means when we use now that index, I'm hinting here SQL Server because with just a few records, SQL Server will not use that non-clustered, it would be too expensive. I'm just hinting here SQL Server. And when we look at the estimated execution plan, you can see now we perform a seek operation. Means we have in the leaf level our records, but we are seeking through the navigation structure to these records. When SQL Server performs a seek, SQL Server never ever logs anything in the navigation structure. SQL Server just logs rows in the leaf level. Means with seek operations, you just have concurrent rows to access your rows in the leaf level. Means with the seek, you can bypass a locked row because you are not scanning, you are seeking. Just think about that. So, let's run the first transaction. Let's run the second one. And now you can see when we perform now our select query, it is not blocking anymore because we are seeking. We seek to that row and we have another row previously locked, but we don't need to read that row physically because with the seek we just bypass it. Means we can retrieve that result. The other session can also continue, and finally we can commit or roll back both transactions without a deadlock. Just think about that. A huge amount of deadlocks can be solved by providing additional non-clustered indexes. As I've said previously, with an additional non-clustered index, you just provide SQL Server additional ways how to get to your data, just additional roads to your data. Means with an additional road, you have no traffic jam, means you have no blocking situations, you have no deadlocking. Just think about that. Make sense? Questions so far? Or are you already deadlocked?
So if you have a where statement with two conditions,
Sorry?
you have a where statement in which you check two columns,
Yeah.
I guess that you need to create a index, a multi-column index, right?
Of course, yeah.
Yeah, you mentioned earlier that all deadlock situations can be retried safely. Is that all situations, or are there some sort of corner cases where you can't just retry deadlock situations?
No. You can retry every deadlock.
So are there any options built into the SQL client drivers that will automatically retry deadlock?
No, you have to code that in your application. Because as you have seen, a deadlock is a situation from which you can fully recover. The deadlock victim is rolled back. When you roll back your transaction, you release your logs. Means the other transaction, which was earlier waiting on you can continue its work, finally end its transaction, and then you just retry yours.
What's the reason behind Microsoft not providing the option to handle those transparently so you don't have to retry?
No idea on that.
Okay.
Are other databases are doing that?
I'm not saying they are, it's just
Okay.
the sort of thing that can be safely retried.
Okay,
It seems strange
yeah.
that they're not retrying it for you and then just reporting success.
Well, the problem with automatic retry would be, of course, you can get into another deadlock.
Sure.
So it doesn't mean that when you retry it once that you have no deadlock, because in the meantime someone else can block you and that other transaction can wait on you. That's the problem. So in that case you just have to code it in your data access layer. Check on error number 1205 and just retry it. Other questions so far? Perfect. I want to show you now a few more deadlocks that can be caused by the isolation level repeatable read. Repeatable read is really dangerous regarding deadlocks. As we have said earlier, repeatable read just means we are holding our shared logs till the end of our transaction so that we have the read stability. I begin a new transaction and I'm reading here some records of the 8th February of 2003. Means SQL Server has on those 6 records a shared log, which we are currently holding till the end of our transaction because we are in the isolation level repeatable read. In a second transaction, I read another range of data. 9th February of 2003. 4 rows. And now we try to update the other range which is currently blocked by the other transaction. Blocking. Mainly, we are doing here the same as in an update execution plan. We are reading data and then we want to change data. As I've said in the beginning, we have an update log for an update execution plan. Imagine what happens if SQL Server would acquire in the reading phase of our update execution plan a shared log. With 2 concurrent transactions, you would have a deadlock. The first one will acquire the shared log, the second one will acquire the shared log, and then everyone tries to convert those shared logs to an exclusive log. The exclusive log can't be granted because the other session has the shared log. Deadlock. Therefore we have the update log, because the update log is not compatible with the update log. Means in that case, in the reading phase, the other update execution plan already blocks to prevent that specific kind of deadlock. Means when we continue with our first transaction and we update the other range which is currently blocked or locked with a shared log from the other transaction, we have a deadlock. Okay? Just think about that. I have here another example. I begin a new transaction. I'm reading again records from the 8th February. And I have a second transaction reading the same records. And now, in my transaction, I try to update those records. Means in that case, SQL Server in the first step acquires an update log, but in that case the update log can't be acquired because we have in the other session here the shared log. And now we try the update again, and boom, we have a deadlock. So imagine you have such a simple transaction in repeatable read. You read data, and finally you want to update that data. It causes you a deadlock. How can you solve that deadlock? Any ideas?
You could take out an exclusive log earlier, or an update log earlier.
Update log on the select statement. Because you're reading that data with the intention to update it later. So when you immediately acquire the update log, then the deadlock will be prevented because you acquire here the update log. Means the other one which tries to acquire the update log is already blocked. So you mainly do the same thing as SQL Server in an update execution plan. So that's very, very important when you are in the isolation level repeatable read. When you read data with the intention to change that data later, acquire immediately an update log to prevent this specific form of deadlock. So when we do that, and we begin our first transaction, we have now an update log. An update log is compatible with a shared log, as you can see here. But an update log is not compatible with an update log. Means when we begin now our transaction and we try to read the same data again, we already block. Update log blocks update log. Same as in an update execution plan. Means now we are waiting here. Now the first transaction can convert those update logs to an exclusive log. We perform our update statement. We finally commit or roll back our transaction. Means we have released the update or exclusive logs. The second transaction can acquire the update log. Then we can continue with the update and complete our transaction. Means we have resolved the deadlock, and again we have decreased the throughput. Because one transaction runs after the other one. That's also the problem. You are more pessimistic. You are working here in a more pessimistic way because you are more restrictive regarding the locking. Means you can resolve the deadlock with the side effect of less throughput. Because one transaction runs after the other one. Previously, both were running at the same point in time, with the side effect of a deadlock when the timing is correct. Just think about that. That's also the problem. As I've said previously, you can't set for every transaction the isolation level to serializable. You would have perfect, consistent data with no anomalies. You have read stability, you have phantom avoidance, and on the other hand, you have a terrible throughput. Because serializable, as the name implies, means that your transactions running serially. One transaction after the other one. Just think about that. Yeah?
Sorry, can I ask? We had this situation in something I was working on.
Yeah.
And another solution which was discussed was taking the select statement out of the transaction, so running it before starting the transaction.
Yeah.
And then detecting on the update statement how many rows were affected
Yeah.
by the update.
Yeah.
What do you think about that?
It's a different way. It's mainly more optimistic.
But the database was set to use a
Yeah.
pessimistic.
It's also possible, of course. Yeah.
Yeah. So it is a kind of, it's a valid strategy.
It's also a valid solution for that. Yeah.
Yeah, okay.
Of course, you can also rewrite it in some way to overcome that specific problem. Other questions? Perfect. Now I show you something very, very nicely. What is that? A deadlock. That's a so-called interparallelism deadlock. Means when you run an execution plan in SQL Server which runs in parallel, I show you such an execution plan. I have here a simple query which produces a parallel execution plan. And parallel execution plan means that you have some operators in an execution plan which can work with multiple worker threads. As you can see here, we have a clustered index can which runs in parallel because we have the two arrows which are pointing to the left. You have here a hash match aggregate which runs in parallel. And finally, you have in every execution plan, parallel execution plan, so-called exchange operators. For example, you have here a gather streams operator which takes your multi-threaded input and produces a single-threaded output. Every parallel execution plan has at least one such an operator because every execution plan must end in SQL Server serially. And the crazy thing about that is the fact that those exchange operators can deadlock internally. There are three different kinds of exchange operators. The so-called gather streams operator, which takes multi-threaded input and produces single-threaded output. We have a second one, what's the name? Distribute streams, which accept single-threaded input and produces multi-threaded output. And the third one is called repartition streams, which accepts multi-threaded input and produces multi-threaded output. And those operators itself can deadlock internally. Not the query itself, the operator itself. And then you can have such nice deadlocks. The most important thing for us is when you have such a deadlock, it's a bug in SQL Server. It's not your bug in query, it's a bug in SQL Server, which will not be solved by Microsoft. Because Microsoft says touching and changing that code is too dangerous. Just think about that. I don't want to know how the code base of SQL Server looks like. They are not fixing such bugs. It's just too dangerous because of the side effects that they can introduce. Because for us, it's very easy to solve that deadlock. How? Run your query single-threaded. Very simple. You have two different ways to make sure that the query runs single-threaded. You can hint SQL Server max DOP option. So when I'm making a max DOP of 1, we are running single-threaded. Of course, the query takes longer because we are just running with one worker thread. In that case, such a deadlock would be history. The other way is to work on your indexing strategy. For example, here we are scanning the complete clustered index in the leaf level. Scanning the clustered index in the leaf level costs us here 46 cost units. By default, SQL Server starts thinking about parallel execution plans when we have a cost factor larger than 5. Means when you're doing less work in your execution plan, by using non-clustered indexes, you can also decrease the query costs, and maybe as a side effect, your execution plan also runs serially. So very simple to solve that specific deadlock. And it's also very, very easy to identify that deadlock. When we zoom in here, you can see that the SPID, the server process ID, is always the same. In that case, it was 436. It's always the same. And normally, you have here in the middle as many processes as you have CPU cores assigned to SQL Server. In that case, it was an interparallelism deadlock, which was running on a system with 16 cores. 2, 4, 6, 8, up to 16. So very simple to identify if you have an interparallelism deadlock, and finally very easy to solve it. Make sure that your query runs single-threaded serially. Question?
So if you have a parallel, an execution plan that has that parallel effect,
Yeah?
will it always deadlock?
No. No.
So you could have a parallel execution path that works perfectly.
Of course, yeah.
And then fail it.
Only in specific rare scenarios, because otherwise Microsoft had to fix that bug. Therefore, I have also here no repro. Only in specific rare scenarios. It doesn't mean that every parallel plan deadlocks.
No, I didn't mean everyone, but if it does deadlock like this will always deadlock.
No. No. It depends on the internal scheduling of the worker threads.
So you could put some code live that runs perfectly with a parallel execution plan.
Yeah, and
then
sometimes
you'll
it
get this
deadlocks.
sometime in
Yeah.
the future.
Yeah.
So it sounds like you should avoid parallel execution plans altogether.
Not really. It's just a side effect. Yeah.
The practical solution would be just to retry as a variable transaction.
Of course. Yeah. Or make sure to run that specific query single-threaded, which would also solve the deadlock. Very simple. Questions? Are you deadlocked? Perfect. So as you can see, when you run multiple transactions, it's very, very easy to go into deadlock situations. We have seen how we can find out if we have deadlocks. SQL Server Profiler, extended events. We have talked about that XML document, the deadlock graph. Also very, very easy to analyze why a deadlock occurred in your system. And finally, I have showed you some specific kinds of deadlocks, why they are occurring, and finally, how you can solve them. Mainly, as I've already said, you will get deadlocks because of missing indexes. So when you work with your indexing strategy, you can also eliminate a huge amount of different deadlocks. Another option, as I've also already said, is to enable read-committed snapshot isolation, optimistic concurrency, because with read-committed snapshot isolation, select statements are not acquiring shared logs anymore, and you can prevent with that approach a huge amount of different deadlocks. How do you like that content? Great. If you want to know more about SQL Server, performance tuning and troubleshooting, I'm coming back to London in the first week of June. I'm running here my SQL Server performance tuning workshop, 5 days about performance tuning, troubleshooting about SQL Server, so a huge amount of different information. If you want to find out more information about the workshop, you will find it on my website. If you give me a business card or mention that you have attended one of my talks at the DevWeek conference, I can also give you a discount of 10%. Okay, so thanks for attending and enjoy the rest of the day. Thank you.